we have started working on phasors, and so far we have done quite a bit. We have shown that if my inputs are all of the form something times e power j omega t, then all voltages, all currents in the circuit will be of the form something times e power j omega t. This is something that we have proved. We have seen, and because everything is something times e power j omega t, we decided that let us cancel out all these e power j omega t's. We will multiply e power j omega t at the fag end, at the end of all the steps. Finally, at the final step, what is the at the next to second last step, we will multiply everything by e power j omega t. And what is the last step? The real part of that, right. You will take the real part of all of this stuff, right. That is the last step. Okay. Before the second last step, you are only going to worry about the complex phasor. Okay. The phasor is the complex number that is in front of e power j omega t. Okay. The phasor is rotating with time, right. It is rotating with time, but we are not going to worry about that. We are only going to worry about what was it at t equal to 0. All right. We only going to look at what was it at t equal to 0, right. The evolution of the voltage you can work out once you know what happened at t equal to 0, right. If you know what happened at t equal to 0, everything else will follow, right. You have got this line which is spinning around at a constant angular velocity omega. That is the plan. All right. Then we saw that these phasors, they are nicely obeying KVL and KCL and all of that, right. They obeyed KVL and KCL, which means that I can now start working only with the complex numbers. Okay. And I can forget about e power j omega t, I can forget about the real part, I can forget about everything. I can just treat the complex numbers as currents, voltages, and they obey KVL and KCL. We proved in the last class. Okay. We also saw that if I have an inductor, then the inductor behaves like a some sort of a resistance. It follows some sort of Ohm's law, where the impedance is j omega L. Okay, we do not call it resistance anymore, right. Likewise, if you have a capacitance, then the impedance corresponding to the capacitor is 1 by j omega c. If you want to call it, if you want to think of conductance, then the admittance is j omega c. Fine, these were new words that we used, impedance and admittance. All right. So, with this we start today. Let us say you have a series combination of R and L. Okay. We already know phasors obey KVL and KCL. So, if I, let us call this I underline. I underline is a complex number. Okay, right now for a few days we will do the underline, later on we will stop putting the underline because everything is complex. Okay. For a few days we will put the underline over there to indicate that, to reinforce that this is a complex number. Okay. I is a complex number. It is actually, what is it? What is the actual current? Real part of I underline times e to the power j omega t, that is the actual current. Okay. But we do not worry about the actual current, we are going to worry about just the phasor, the complex phasor I. What is going to be the drop across the resistor? I times R, that is the drop across the resistor. What is going to be the drop across the inductor? L? No more L di by dt, that zamana, that age is over, right. We do not want, this is an impedance, use Ohm's law, j omega L times I. What is the total drop? I into R plus j omega L, which means that the complete series combination is an impedance of value. Problem? Some problem? No, no problem. So, the complete series combination is an impedance of value R plus j omega L, fine. It is just series parallel, right. Whatever you learnt in class 11, class 12, right. If I put impedances, if I have Z1, Z2 and Z3, three impedances in series, what is going to happen? What is the net impedance going to be? Z1 plus Z2 plus Z3, right, and Z can be a complex quantity now, right, not purely real, not purely imaginary, it can be anything, anything plus anything. Is this okay? And you can do put things in parallel also, right. If you have Z1 and Z2 in parallel, what will you get? So, let us put things in parallel. Okay, let us put two things in parallel. Let us apply a voltage V, underline. What is the current this way? V upon R. And what is the current this way? V upon j omega L. So, what is the total current? Fine. Okay. So, the net impedance is 1 by R plus 1 by j omega L, just like you have put the two impedances in parallel. This is the same result, right. Okay. So, all the stuff that you have learnt earlier, series, parallel, right, they all apply, just that you now have to expand your mind and deal with complex numbers. Okay. They are following the same rules, exactly the same rules. And why is that happening? Because the phasors are obeying KVL and KCL nicely. All right. Okay. Let us now do something more. Let us analyze a circuit. Okay. So, let us analyze this circuit. What is your favorite method right now? Mesh, node, voltage source. So, therefore, what do you want to do? Let us do mesh method. Fine. What do you want to call this current? So, 3 loop currents. First one is what? Top one is what? I 1 underline, okay, to indicate that this is a phasor. Second one is I 2 underline, and third one is I 3 underline. All right. And the way we write our mesh method equations, we are going to get 3 equations for the 3 currents, and whenever we have 3 equations, we write them as a matrix, in the form of a matrix. And let us fill up this vector first. This vector will have I 1, I 2 and I 3. Is this okay? So far so good? Okay. Loop number 1, the sum of the drops, the sum of the voltage drops is equal to 0. This is KVL. So, sum of all the voltage drops is equal to 0. So, drop across L 5 is what? J omega L 5 times I 1. Drop across L 3 is how much? J omega L 3 times I 1 minus I 3, fine, and drop across R 1 is R 1 times I 1 minus I 2. Is this fine? Nothing much. Whenever you are encountering, it is the same old thing. Every time you are seeing an inductor, instead of writing the value of the inductor, you are writing j omega times the value of the inductor, that is all, right. Otherwise, it is the same old thing. Okay. Loop 2, drop across V naught is minus V naught, which goes to the right hand side and becomes plus V naught. Okay. Then drop across R 1 is I 2 minus I 1 into R 1, and then drop across C 2 1 upon j omega C 2 into I 2 minus I 3. So, I am not going to write it as 1 by j omega, I am going to write it as minus j by omega C 2, if that is okay with you. Instead of writing 1 by j omega C 2, I have written it as minus j by omega C 2, just for fun. Okay. And what will come in the third column? Plus j by omega C 2. Fine. Then last row, what will I write in the third column of last row? okay, right hand side is 0. Third column minus j by omega C 2 plus j omega L 3 plus R 4, and corresponding to the second column and first column minus j omega L 3. Yeah, 1 by j is minus j. Is it okay? And then who is going to invert the matrix? Computer is going to invert the matrix. Have you downloaded some software to do this stuff? Please do download. Okay. You can either use MATLAB or you can use Octave. I suggest you use Octave because Octave is free and the syntax is the same as MATLAB. So, you will not be missing out on anything. Syntax is exactly the same, just that Octave is free. So, might as well just use Octave. Support is similar. Okay. So, please download Octave, or if you insist you can download MATLAB, but MATLAB is licensed software. So, be careful. How will you enter in Octave? So, Octave will give you a screen and then there you will have to enter the matrix. So, you will have to say A is equal to j times omega times L 5 plus j times omega times L 3 plus R 1 comma then minus R 1 comma minus j omega L 3 and then next row is given with a semicolon, and like this you will have to enter the whole thing, then close the bracket. That gives you the this whole matrix A, okay. And then B is equal to 0 semicolon V naught semicolon 0, and then what is your answer going to be? I 1, I 2, I 3 is therefore going to be I or whatever. So, what will you do? Inverse of A times B, this is what you have to compute, and this will list out values of I 1, I 2, I 3. Fine, do this please. Okay. You have to of course fix values for all these things, but that is okay, you can choose whatever value you want, right. It will not do it algebraically. It can do it algebraically also, but then you have to load the appropriate package, you have to define those as symbols. I do not recommend doing it algebraically at this point in time, there is no need, right. Just put in some values and be happy, right. Use the tool, start using the tool. Okay, great. Now, I am going to throw in some complications over here. You will be able to do it with node voltage also, the same thing, straightforward, just ground one of the nodes, define all the potentials V 1, V 2, V 3, correct, and then carry on, right. You will be able to do the same thing with node voltage method. Okay. Now, I am going to throw in some complication over here. I am going to put some dots. What does this mean? What does it mean? Mutual inductance. You are familiar with the, we have discussed mutual inductance. Yeah, we had discussed a long time back mutual inductance. Okay. But let us discuss it again. Recap. Okay. So, the convention is that whenever I use small letters, I am talking about something happening as a function of time. Okay. That is the convention. Small letters, small I 1 means it is a function of time. All right. Whenever I use capital letters, I am talking about a dash. A phasor. Okay. Capital V indicates that I am talking about a phasor, complex numbers. So, capital letters indicate that we are talking about a phasor, it is simply some complex number, constant. Fine. Any questions? No. Good. All right. So, when I have written everything in small letters, it means that we are working in the time domain. Sometimes we work in the time domain, sometimes we are now in phasors are not in the time domain, they are in the frequency domain. Okay. You shift your perspective from time to frequency. All right. You are looking at something which is moving with time at a certain rate. What is the rate? The phasor is rotating at omega, angular velocity. Okay. So, whenever that happens, you have shifted from the time domain to the frequency domain. All right. So, right now I am working in the time domain. In the time domain, I know very well what is V 1 of t, L 1 times d I 1 of t upon d t, and we also know that V 2 of t is L 2 times d I 2 of t upon d t. Okay. Now, we put these two dots and we incorporate a mutual inductance. Okay. What does this mean? This means that these two coils, these two inductor coils were wound on the same iron core. The flux going through one is also going through the other one, at least a part of it. Some flux that is going through one of the two coils is also going through the other coil and vice versa. Okay. If you read Griffith's electrodynamics, there is a book, it is there in the other course. Which course? Yeah. Okay. So, if you did the physics course, they followed the Griffith's book. I hope they followed the book. There is a section in the book which proves that this, the fraction of the flux of coil 1 that goes through coil 2 and the fraction of the flux of coil 2 that goes through coil 1 are the same. There is one section that proves that. Okay. And then you define m to be equal to that fraction times square root of L 1 L 2. Okay. K is a number, k is between 0 and 1. Fine. This you have proved in Griffiths. If not, please check. Please check Griffiths. There is a section dedicated to this. Small section, half page. All right. So once this happens, so therefore, m is the same for both, right. This constant m is the same for both flux in coil 1 causing EMF in coil 2 as well as current rate of change of current in coil 2 causing EMF in coil 1, right. This factor is going to be the same. So, what we are going to do is we are going to add this factor. Okay, this is the plan. This is how we describe a mutual inductance. Fine, ordinarily. Any questions? Okay. Now, what we are going to do is, to start with, we know that when we are operating at sinusoidal steady state, then all the voltages, all the currents, they are of the form some complex number times some complex. So, all this V 1 is going to be some complex V 1, right, some complex V 1 times e to the power j omega t. That is what V 1 is going to be, right. And I 1, what is that going to be? What is I 1 going to be? Small I 1, some capital I 1 complex times e to the power j omega t. And I 2 is going to be some capital I 2 complex e to the power j omega t. Okay. Let us do the first one first. So, help me with the derivative. Yeah, what do we do with the derivative? D by dt, what do we do? J omega come out, right, I 1 also comes out, and that is it. Okay. And similarly, this becomes j omega m times I 2 e power j omega t. Fine. And what is the next step? Cancel out e raised to j omega t. All right. My equation is becoming simpler and simpler. I basically get V 1 is equal to j omega L 1 times I 1 plus j omega m times I 2. Okay. What about the second equation? Second equation will be V 2 underline is equal to j omega m times I 1 underline plus j omega L 2 times I 2 underline. Fine, this is the pair of equations. Fine, great. What if I did this? What if I put the dots the other way? Now, what is going to happen? In place of m, you will have minus m. Why do you say so? Opposite polarity. Okay. I what you are saying is totally correct, but what you could do is you could redraw this by flipping it. Okay. Just flip it around, flip this part around, right, turn it upside down. You basically get okay, V 2 becomes upside down and I 2 goes out. That is what happens. Fine, flip it around and now you write the same equations as you had earlier, right. So, you had earlier V 1 is equal to j omega L 1 times I 1 plus j omega m times minus I 2. Okay. And you get minus V 2 is equal to j omega L 2 times j omega L 2 times minus I 2 plus j omega m times I 1. Okay. Effectively, what you have got is V 1 is equal to j omega L 1 I 1 minus j omega m I 2 and V 2 is equal to minus j omega m I 1 plus j omega L I 2. Okay, effectively, right. Effectively, it appears that the mutual inductance is negative in this case, right. It appears as if you have flipped the sign of the mutual inductance, but you have not really done much. Okay, it is the same thing. Okay, I need you to appreciate that it is the same thing, it is not anything fancy that you have done. Okay, it is just a redrawing, relabeling of what is V 1, what is I 1. Okay. Let us go back. Okay. Now, we have to solve this and this solution is already available to us, right. This we had written when m was equal to how much? 0, when there was no coupling. Okay. The coupling coefficient was equal to 0, this is what we had written, no coupling between the two inductors. Now, the two inductors have been coupled, okay. They have been wound on the same iron core, or the flux through one goes through the other, that is all. All right, what is going to happen? You want to start with the first line. Let us look at the first line. First we have I 1 current, right. It creates a drop j omega L 5 times I 1, correct, this one, but it also has a drop because of the other one, the mutual, right. So, if you notice, all right, let us put some symbols. So, I have put dots, let us put these triangles over here. Okay. Just to make things clear, the dots look similar and the triangles also look similar. Okay. So, if I say that the dot terminals are coupled, then the triangle terminals are also coupled, the opposite terminals are also coupled, fine. Okay. So, the dots are coupled with each other, triangles are coupled with each other. The current entering the triangle in L 5, what is it? I 1. What is the current entering the triangle in L 3? Entering the triangle, I 3 minus I 1. Okay. So, what will be the extra drop created on L 5 across L 5? J omega m times I 3 minus I 1. This is the extra drop created on across L 5, okay, for current I 1. Understood? So, I am going to add j omega m here and I am going to subtract j omega m here. Fine. Okay. Now, let us look at L 3. L 3 ordinarily has some drop. Now, there will be an additional drop because it is coupled to L 5. Okay. The current entering L 3 at the dot is how much? I 1 minus I 3, which is fine. At the dot, what is the current entering L 5? Minus I 1 is the current entering the dot at L 5. So, therefore, the extra drop is going to be minus j omega m times I 1 or j omega m times minus I 1. Fine. Is the first equation okay? Anything else will change? Yeah. Second loop, nothing changes, right. I have R and C and voltage source. So, there is nothing much happening. The third loop, let us look at the third loop, and in the third loop specifically let us look at L 3, right. So, if you go through I 3, you are following I 3 in the third loop. So, you hit the triangle first, right. I 3 First you see the triangle L3. So, what is the current in L5 at the triangle? Current entering the triangle at L5. I1 is the current entering the triangle at L5. Okay. So, there will be an additional drop of how much? J omega m I1. Fine. Is the matrix symmetric? Yes or no? Yes, the matrix stays symmetric. All right. Why is it staying symmetric? Because the mutual inductor is a dash component. Passive component. I do not know these terms, bidirectional. I have no idea what it means. Okay. So, mutual inductance is a passive component, because of which the matrix remains symmetric. If you did not have passive components, then there would be a question of asymmetry in the matrix. If you had VCVS, then there is a question, right, is the matrix going to be asymmetric. But since there is no such VCVS etc., no active components, the matrix is going to remain perfectly symmetric, even when there is a mutual inductance. Is this okay so far? Any questions? Question? No? Good, because you know, things can get complicated, right. Things can get very complicated very easily, especially with these mutuals, right. You could even wind 3 inductors on the same core. So, for example, we could potentially have another one over here. Let us not change this one, this is nice. I mean, you could replace that one with another inductor wound on the same core, and now there are 3 that are coupled with each other. You will have M12 between 1 and 2, you can have M23 between 2 and 3, and you can have M13 between 1 and 3. Okay. What are we going to do? We are going to give you 3 inductors all coupled to each other, and then now you are asked to solve the circuit, and then you will have to solve. Fine, you will be able to do it? Should be, right? There is no reason why not. It is just more and more terms that are getting added into the same KVL. Always start with the KVL which does not have mutual, right. First write it out without the mutual, then throw in the mutual terms, right. That is how things will look straightforward. If you try to solve it from scratch, it might be too intimidating. The other tip is that when you have these mutual inductances, the preferred method is mesh method. Okay. Avoid node method, because node method might be a little difficult. Fine. And basically you will not be able to write this. This is right. This is a KVL effectively. In the node method, the KCL, it is going to become a little difficult to operate in the node method with mutual inductances. So, avoid node method, try to use mesh method when you have mutuals. Any other question? Will you be able to do such questions in future? All right, you are doing fine. Uh, Telegan's theorem, all the voltages. So, if I have a circuit and I know all the voltages and I know all the currents, then dot product is going to be equal to 0. Fine. If I know the voltages at t equal to 0 and if I know the currents at t equal to pi by 2 omega, rather omega t equal to pi by 2, if I know all the currents, then what about their dot product? 0. Fine. Okay. So, if I have a phasor V at t equal to 0, what is the actual voltage? Real part of V. This is the voltage at t equal to 0. Okay. Now, this rotates, let us say it rotates by 90 degrees and at t equal to at omega t equal to pi by 2, this is at t equal to 0. So, whenever you have a phasor, the voltage, the actual voltage at t equal to 0 is just the real part of the phasor. Okay. What is the actual voltage when omega t is equal to pi by 2? How much is it? No, no, the actual voltage is always the real part. Real part at the original position is real part of V. Minus imaginary portion of V is this one. Fine. And similarly, at omega t equal to minus pi by 2, what is the actual voltage? Plus imaginary part of V. Fine. So, you can, so you see what is going on. So, at t equal to 0, the actual voltage of the phasor okay, at omega t equal to minus pi by 2, is the imaginary part of V. Fine. Omega t equal to plus pi by 2, I get minus imaginary part of V. Omega t equal to pi, no, minus real part of V. Fine. Your vector is rotating, all right. Always the actual voltage is the real part of that vector. Okay. You can think of it as the projection, the shadow of the vector on the real axis, right. You shine light from the top, the shadow of the vector on the real axis is the actual value. Fine. Okay. So, what am I getting at? I am getting at the following, that if I take all the real parts of all the, suppose I have a circuit, right, I have a complicated circuit and it has voltages V I are all the voltages, these are all phasors, fine, and I sub I are all the currents, these are all phasors, fine, these are all phasor quantities. Now, the actual voltage at t equal to 0, the list of actual voltages at t equal to 0, what are they? They are the real parts of V I. Okay. It is the list of actual voltages, and similarly the list of actual currents at t equal to 0 are the real parts of I. Fine. And therefore, by Telegan's theorem, sigma of the sum of real part of all the voltage phasors multiplied by real part of all the current phasors is equal to 0. Fine. But it is the same circuit, the graph is not really changing. So, therefore, real part of V I times imaginary part of I sigma is also equal to 0, because it is the same graph, right. I just changed the time, the currents are now measured at omega t equal to minus pi by 2, right. The voltages are all measured at omega t equal to 0, the currents are all measured at omega t equal to minus pi by 2. Therefore, the product is equal to 0, sum of products is equal to 0, and similarly fine, this is also true, and what else is true? This is also true. So, all 4 of these statements are true. Is this okay? What else is true therefore? V into I. What is V into I? This is V I into I is nothing but real part of V I plus j into imaginary part of V I into real part of I plus j into imaginary part of I, right. So, that is equal to real times real plus j times imaginary V I times real I plus j times real V I imaginary I minus imaginary V I times imaginary I. And if I do the sigma of this over all the components, all the branches, then it is the sigma of this, which is the sigma of all of these, and that is therefore going to be equal to 0, because each of these terms are individually equal to 0. Fine, everything is 0 0 0, right, each of those summations are 0. Okay. What about this one? How about what is that star for? Conjugate, complex conjugate. Also is going to be 0, because this is nothing much. This is real plus j imaginary, real of V I plus j, sorry, j imaginary V I times real of I I minus j imaginary I I. And since we have proved that real times real is equal to 0, sigma real times imaginary is also equal to 0, imaginary times real sigma is also 0, and imaginary sigma is also 0. This is therefore also going to be equal to 0. What about this one? Also 0, right. And lastly, what about this one? 0. Okay, all of these are equal to 0. Fine. Okay. Just suppose I fix, I have a certain value of omega, and let us say this is 5 ohms, and this inductor, this is j times 10 ohms, and this capacitor, this is minus j 3 ohms. Okay. You figured out by now, capacitor will have minus j some. Okay. Units are ohms or no? What is the unit of impedance? Ohms. Are you sure? Omega times L, what dimension does it have? Huh? It follows Ohm's law, so hopefully, yeah, but can you check omega times L? What are the dimensions of omega? What are the dimensions of L? Omega is 1 by seconds, and L, what is L? Energy by current squared, very good. Okay. Energy by current squared, and what on earth is energy? Voltage into current. No, voltage into current into time. Voltage into current into time is energy upon I squared. Okay. So, T cancel out, I and I squared. So, you get V by I. So, you get ohms. Fine. What about 1 by omega c? Hmm? Omega is 1 by seconds. So, this becomes time, and q is equal to C V, right. Charge is I times current. So, C is V by Q, 1 by C is V by Q. Okay. By charge, and charge is current into time, and time cancels out. Okay, so this is also ohms. All right. So, both of these are in ohms, just that whenever you have inductor it is going to be J times something in ohms, and whenever you have a capacitor it is going to be minus J times something in ohms. Fine. I mean it automatically means that the value of the capacitor as well as the value of omega are given, right, together they have been mentioned. All right. Suppose I tell you that this current is 1 ampere, or let us say it is 1 angle 0 degrees. Okay. What is going to be the voltage across this combination? Quick way to do is, I mean you can do it orally, you do not have to think, right. These three are in series, 5 plus J 10 minus J 3 is equal to 5 plus J 7. So, it is 5 plus J 7 into 1 angle 0 degrees, that is all, that is the answer. Okay. But nevertheless, let us just see, look at it graphically and see what happens. Sometimes graphs give us some intuition. Okay. All right, 1 angle 0 into 5 ohms. So, I have 3 drops over here. There is a V R, there is a V L, and there is a V C. Okay. All 3 are phasors. So, V R is 1 angle 0 times 5 ohms, and that is going to be simply a vector of 5 units, right, along the real axis. Fine. V L, what is V L going to be? J times 10 units. Okay. So, it is going to be a vector, let us reduce the size of this. So, this is going to be a vector of size 10 units. Fine. And lastly, what do we have? V C. V C is going to be a vector of minus J 3, right, minus J 3 times 1. So, it is going to be a vector going downwards by 3 units. Okay. And now, what is the overall going to be? Overall it is going to be, you have to do the vector addition, right. You know how to add vectors, you can triangulate, right, you can draw these lovely triangles, or what do you call it, parallelograms. This is your final answer. Fine. Any questions? So, we are following the same principles as your mechanics, right, adding vectors, the same stuff is happening here, right, just that our vectors are complex numbers and two dimensional only. There was the possibility of having I, j and k, no k is involved over here, there is only I and j. Actually, there is no I and j, there is only j, there is real part and imaginary part. Fine. Okay. Now, suppose we had a different kind of problem. Suppose I had the problem as suppose I gave you that this same circuit is there, but I have applied 1 angle 0 degrees as the voltage. Now, what is going to happen? So, earlier what did we do? Earlier we pushed 1 angle 0 degrees into the circuit and measured the voltage. Now, I am saying suppose this is the voltage, what is the current? Okay. By the way, notice something, notice over here that the voltage across the inductor is always going to be in front of the current through the inductor. So, the current through the inductor was 1 ampere, right, and the voltage was in front, it was 90 degrees ahead, okay, and the voltage across the capacitor was 90 degrees behind, was trailing behind. Okay. So, if you draw the sine wave, then you will notice that the voltage is running ahead of time, ahead of the current for the inductor and behind the current for the capacitor. So, if this is the sine wave for the current, then the voltage of the inductor is running 90 degrees ahead and the voltage across the capacitor is running 90 degrees behind. Okay. We say that the current through the inductor lags behind the voltage. So, this is the term used, current in L lags behind, it is lazy, it lags, okay, L, this L lags, current in L lags behind the voltage. Fine. Unfortunately, this L is not going to work so well in the next statement. The current in the capacitor leads the voltage. All right, these are the two statements used. Okay. What do you have to remember? You have to remember that inductor current always lags behind, right. Why does it lag behind? Because it starts with the letter L. Inductor is L, L stands for lazy, right. So, inductors means they are lazy and therefore, the current lags behind the voltage, and likewise opposite the capacitor, the current leads the voltage, it is running ahead in time. Okay. This general words, sentences that we use all the time. Okay, never mind, let us go back to what we were doing. So, we had pushed a current 1 ampere and then measured the voltage across each of the components, added them, vector addition, right, found the voltage, net voltage. You need not have done all of this, you could have simply used your calculator. 5 plus J 10 minus J 3 is 5 plus J 7, right, and this is 5 units this way and J 7 units that way. This is 5 and this is J 7, and your net result is 5 plus J 7. Okay. You could have done it that way as well, you will get the same answer nevertheless. What we are now going to do is, now imagine that you did not push a current, but you applied a voltage instead. Now, what is going to happen? Now, what we are going to do is, we are going to turn this VR plus VL plus VC, we are going to turn this graph, right, this whole graph, let us turn it. Is there a way to rotate it? We will have to rotate it by redrawing. I will have to redraw the whole thing, but what I am trying to do now, I am trying to draw the axis in this fashion. This is going to be my axis. I am redrawing the axis aligning with which one? Total vector. Okay. So, VR plus VL plus VC is going to be aligned over here. All right, and this is going to be 1 angle 0. Remember, this is 1 angle 0 in the new problem, correct. This is 1 angle 0 in the new problem. And what is VR going to be? VR is going to remain the same. VR is still going to remain this one. All right. What is VC going to be? VC is still going to remain the same. It is going to remain this one. And what is VL going to be? It is still going to remain the same. It is going to remain this one. Okay. All I did was, I turned the graph, the reference of the graph, and realigned it with VR plus VL plus VC. It is as if I said that let us choose a different time frame. Earlier, whatever omega t was, right, let us offset our time and say that the new time is going to start at this angle. This is the starting of time, t equal to 0. So, we are simply calling t equal to 0 this new point, new line, new alignment. Is this okay? Not okay. And what is VR plus VL plus VC is now going to be called 1 volt, right. This is what has been applied, 1 angle 0. So, this is equal to 1 volt, right. Earlier it was how much? Root over 5 squared plus 7 squared. Now, that is going to be called 1, that has a length of 1. So, what is going to be the length of VR? Earlier whatever length it had, that divided by root over 5 squared plus 7 squared. Earlier it had a length of 5. So, now it is going to have a size of 5 divided by 5 squared plus 7 squared. Okay. V L, earlier it had a length of 10, now its new length is going to be 10 divided by root over 5 squared plus 7 squared. Okay. Earlier V C had a length of 3, now its length is going to be 3 divided by root over 5 squared plus 7 squared. All right. Earlier this angle, how much was this angle? Tan inverse of 7 by 5. This was tan inverse of 7 by 5. That was the angle over there, right. So, this angle is going to be preserved. So, V r, the new V r is going to be equal to 5 by root over 5 squared plus 7 squared angle minus tan inverse of 7 by 5. Understood? V c, the new V c is going to be 3 by root over 5 squared plus 7 squared angle minus tan inverse 7 by 5 minus pi by 2, and new V L is going to be 10 by root over 5 squared plus 7 squared angle minus tan inverse 7 by 5 plus pi by 2. Understood? Of course, you could always have computed this with your calculator, it is nothing much. Okay. But how would you have done it? The current is going to be 1 divided by 5 plus J 7, that is the current. Okay. And that current into 5 ohms. So, the voltage across 5 ohms is going to be 5 divided by 5 plus J 7, V L is going to be J 10 by 5 plus J 7, and V C is going to be minus J 3 over 5 plus J 7, and you have to verify that these two are the same, this and this, right, these two are the same thing, please verify. Questions? It is time to stop. We have covered a lot of ground. Tell me, ask me questions if you want, if you have doubts. Questions? No? Clear? Everything is clear? Clear so far? Okay, thank you.